This is projectile motion. Previously, we learned about free fall, when an object is affected only by the acceleration due to gravity, like this ball. Here we'll see a ball thrown up in the air. It starts moving quickly until it reaches its peak. So when he first threw it, it had its maximum upwards velocity. The acceleration, though, was pulling down on it. When velocity and acceleration are in the opposite direction, here we have a positive velocity and a negative acceleration, the object's going to slow down. At the top of its throw, where the ball is now, the object has a zero velocity. But gravity is still pulling down on it, so it still has a negative acceleration. Then it's going to fall down. Negative velocity and negative acceleration means it's going to be going faster and faster. That's free fall. So that's free fall. We've seen the ball go up and go down. We've talked about other objects falling down or going up and then falling down. They're affected only by gravity. But that's not how we usually deal with things like baseballs or softballs or cannonballs or rocks. Today we're going to be talking about projectiles. Let's look at an example of projectile motion with the greatest throw in baseball history. Here we go.
This fly ball appears deep enough to score Bando. But right fielder Joe Ferguson intercepts and uncorks.
Oh my God! And he's out.
Bando is out.
Amazing play, amazing. Now watch the path of the ball carefully when he throws.
If such a fly ball like that was a hit with a guy on third base, that if I could get there, I'd take it. And it probably looked like Jimmy Lynn was getting ready to catch the ball. And just before I caught the ball, I told him that I have it, and he said, "Go ahead, take it." And fortunately,
he throws. The ball goes up, and then it starts coming down, down, down. But the whole time, the ball is also moving horizontally.
Joe Ferguson's 300-foot bullet-like throw is certainly worth watching one more time.
Enjoy the music. That's free.
Ferguson's incredible heroics keep the Dodgers' deficit of 2 runs going into the bottom of the ninth.
So, that is a projectile. Let's talk about projectile motion. First of all, a projectile is an object that's thrown or launched in the air. Instead of going straight up and down like an object in free fall, we now also have a horizontal component to it. Projectile motion is simply the path that those objects take once they're thrown or launched. We still have gravity pulling down on these things, but they're also moving side to side. And if there's no air resistance, then those projectiles will have a parabolic path. Let's take another look at a parabolic path. This is an awesome water fountain, and it's a good example of objects in free fall. The streams of water have very little air resistance, and you can see that parabolic shape. You probably graphed a bunch of these in math class. So, projectile motion. Projectiles look a lot like objects in free fall, but they also have a horizontal component. Now, when we dealt with vectors at an angle, we broke them up into their vertical components and their horizontal components. Just like that, we're going to treat the horizontal motion and the vertical motion separately with projectiles. Now, you know what the acceleration due to gravity on Earth is. At least you should know. Psst, it's 9.81 meters per second squared. Because of that, vertically speaking, projectiles act, again, just like an object in free fall. And we can use the same kinematic equations we did for free fall when we're talking about projectiles. Here's the really nice thing about projectiles. Horizontal motion is constant. The velocity does not change if there's no air resistance. So your horizontal displacement, delta x, equals the horizontal velocity, that's what that v sub x is, times the time. This is just another version of the average velocity equation. We'll talk more about these equations in a minute. Before we get to that, though, I want to talk about wind resistance. Here on Earth, we have something called an atmosphere. Now, this is a good thing because it allows us to not die. On the other hand, it's not good for physics. When we do our calculations, it makes things very complicated. Consider this soccer player. When they head the ball, if there was no air resistance, that soccer ball would follow a perfect parabola. However, because of the atmosphere and the air around it, anytime that soccer ball wants to move, there's going to be wind pushing against it in the opposite direction. This is like when you're driving in your car and you put your hand out the window and you start playing the airplane game where the wind blows your hand up and down. That's because of wind resistance. And it makes our shape not a perfect parabola. So we ignore it. Yay! That makes our calculations a lot easier. So let's take a look at another projectile. This one might be a little more familiar. Here we have a catapult made by last year's class, and we're going to fire it. Take a look at the tennis ball as it goes. So you can see that the tennis ball was fired and it went up and it came back down. That's good. Gravity's still working. And it also is moving right to left. Let's take one more look. You're ready. Two more looks. Okay. What we can do with a program called Logger Pro, which hopefully you guys will have by the end of the semester, is analyze the position of the tennis ball on every frame of that video. So with this program, I can slow down the video and I can mark the location of the ball throughout. So frame by frame, I've marked where the tennis ball is, and this program will actually capture that data and take a look at it. Here's my origin. The ball is moving right to left, so horizontally it has a negative velocity. The ball goes up and then comes back down, so it starts out with a positive vertical velocity and then switches to a negative vertical velocity as it falls. Once I've gathered all that data, I can graph it in a position time graph. The red dots show the horizontal position over time, and the blue dots show the vertical position over time. Here's the cool part. Remember, the slope of a position time graph is equal to the velocity. So this program will actually calculate the slope between each point and show me what the velocity is. So let's look at the horizontal velocity over time. Here it is. It's a negative velocity. Up here is 0. Down here it starts out about negative 5.5 meters per second. And it's slowing down a little bit as it goes. It ends up at about negative 4.5 meters per second. Now before I told you that the horizontal velocity of a projectile is constant. And that's true, but that's only if there's no air resistance. The tennis ball we use on the catapult, it has some air resistance. It's not very dense, and it's got all those fuzzy wuzzies on the outside, so that's going to capture the air and help it slow down. But it's fairly horizontal here. The velocity is fairly constant. It's around negative 5 meters per second throughout. The vertical velocity is a different story. Here you can see that the vertical velocity starts out positive, and it has a fairly steep drop-off. So now it's slowing down, slowing down, slowing down until it hits this point where it's 0 meters per second. Right here, the ball is at its peak. It's at its highest point. And then it starts to fall downwards, and it starts out going slowly downwards, and the velocity gets more and more negative as it falls faster and faster. The slope of a velocity time graph equals the acceleration. So if I can find the slope of this line, and it's a fairly straight line, the points aren't perfect, but it's fairly straight. If I can find the slope of that, that should give me the acceleration due to gravity on the ball. So this program allows me to find that line automatically. I'm going to go with a linear fit because I think it's a constant acceleration. So the program has put in the best line for a fit, and it says that its slope is negative 9.51 meters per second, or meters per second squared. That's pretty close to our accepted value for gravity of negative 9.81 meters per second squared. The reason it's a little less is probably due to the air resistance. So, what have we learned? Well, we know the projectiles act just like an object in free fall, but instead of moving just up and down, they also move horizontally at the same time. We can ignore air resistance with projectile motion, just like we do with free fall. And the horizontal velocity is constant, so there's no horizontal acceleration for a projectile. The vertical motion does have acceleration. That's the acceleration due to gravity, which here on Earth is negative 9.81 meters per second squared, and we can use the normal kinematic equations to figure out the vertical motion of the projectile. That's it for today. Thanks for listening. McCloy out.